How you doing? We're lively. Great. So, does anyone have a Surface Pen that they could lend me? I left mine in the basement, I'm pretty sure. Okay, if not, it's okay. But if you do have one, Thank you. Perfect. Okay, make sure you get it back. These are valuable. Okay. Today we're going to talk about stress and strain. But before we do that, I'd like to do a little bit of a review and then try to answer maybe a question for the inquiring mind. Well, at least one of you was inquiring about this. Okay. So in the last session, you had the opportunity to get familiar with Hooke's law and get an idea of what it means for axial loading to lead to displacements or deformations of members, to look at systems with multiple beams in them or multiple bars in them with rigid beams, and also get a taste of indeterminate systems. Okay, so what I'd like to do, this question came up over email, and I'd just like to do a few little things here at the beginning to, I don't know, just get us to think a little bit more about what it means for springs to be in series or parallel, okay, and how that might relate to some indeterminate problems that we're trying to solve. Okay, so if you saw a bar that looks something like this, with two sections, and there's a force there, and you've got, let's say, a K1 and a K2. And I say, okay, I'm interested in the delta, and I want to know the effective spring constant that relates the delta and the applied force. What would you say here? What would you say? What is K effective going to be? Yes?
Is it 1 over K1 plus 1 over K2?
Okay, so 1 over Kf is going to be equal to 1 over K1 plus 1 over K2. Yes, okay? And another way that we write that is that K effective is equal to K1, K2 over K1 plus K2. If I make one of these bars longer, okay, and so first off, okay, this is, again, going a little bit off your intuition and not off of the mechanics that we're going to cover shortly. Not today, but short. Well, I guess we're covering it now in a sense. But if I make one of these bars longer, or let's just say that I went from 1 bar to 2 bars, okay, so I made that 1 bar longer, does the coefficient of the spring rate, or the spring rate, or the spring coefficient, or the spring constant, does that go up or down? If I have the same material and I just make it longer, does the spring rate go up or down? It goes down, right? Okay, it gets squishier, right? It's like if I have one mattress and I'm sleeping on it, and I put another mattress on top of it, right? It's going to be squishier, right? It's like if you get a certain amount of foam, right, and you're going camping, you know, you probably have a thinner mattress, and obviously, depending on, you know, the properties of the material that are being used in that mattress or that foam support, you're not going to get the same nice squishy feel that you have on, you know, your thick mattress in one of your, you know, dorm or and hopefully your homes, okay? Dorm rooms or homes. Okay, so just to give us a little bit of intuition about what's going on here. You know, I think you're probably like, oh, okay, if I draw this one, and I put a force on it, and I'm interested in the delta, and I have a K1 and I have a K2, all right? First, these springs are in series or parallel? Parallel, right? Okay, and so you have an intuition, right, that if I have one spring opposing the force that I'm putting, and I put another spring in there and it's opposing the force, right, that's going to do what to my spring constant, or my spring rate, or my spring coefficient? It's going to increase it, right? It's going to make it stiffer, as it were, as whatever we say, okay? So we have an idea that in this case, the K effective is, as we've talked about, is just going to be the summation of these two, right? And so this goes to the idea, I think we talked a little bit about it, mostly in terms of the amount of force or load that a bar can support in our first session together. That was, okay, will it break or not, right? But also we have an idea that if I increase the cross-sectional area of my bar, okay, it's going to have a higher stiffness, right? And this kind of bears out. You can think, oh, I have one trunk of a tree, but if I put a lot of trunks of trees together, right, the overall stiffness, the amount of deflection I'm going to see if I jump up and down on it is going to be less. Okay, so the spring rate, coefficient of spring, the spring coefficient, however we want to call it, it goes up. Okay, now, this is now talking a little bit about one of the indeterminate systems that we saw, and this is in slight response to an inquiring mind. Okay, what about that? Are the springs in series or parallel? Okay, good. I got the conflict I was seeking. Okay, some people are saying parallel, some people are saying series. Okay, so maybe let's look at this a couple different ways. All right. One, this is the fast slickaroonie method. All right, that people don't like it when I just do. All right, in past experience, I say, look at this. This system looks just like this system. You tell me, why would I do that? Why can I do that? So what is this bottom system? Well, this bottom system is obviously springs in parallel, right? But how can I go about doing this loop-de-loop? Yes?
Because you have the two constraints on the side.
Well, yeah, absolutely. It's because I have the two constraints on both sides. Let's go a little deeper, though. Go a little deeper, yes. So that's why. What do we know about both of those bars in terms of how they react to an applied force where I'm putting it? Are they both opposing the force? Is one opposing, is one not opposing? What's happening? Yes? Yeah, so one is being put in tension, right? The one on the left is being put in tension, and the other one on the right, at least the way I drew the force, okay, it's going to be put in compression. In terms of the stiffness of each of these elements, does it really care if it's in compression or tension? No, it doesn't. Okay? So both of these elements are opposing that force that I'm putting on the system. Okay? So that's one clue. What about the displacements? So you said one's in tension and one's in compression. If I look at the magnitude of those displacements, are they different for each of the members? Are they the same? Well, they're the same, right? It's almost a rhetorical question, right? They're the same, okay? And that is one of the salient attributes of what we mean by springs in parallel. Okay? This is, I may not have emphasized this enough in the videos, right? But springs in parallel can experience different forces, potentially different forces. while and while their displacements are equal. Okay? Springs in series have the same forces. So like if I go back to this one up here, the force, what's the force inside of this element? Or this section? What's the force inside of this section? Well, right, we did that. Right? Remember we did method of slices last time or 2 times ago, right? And when we did that, right? Oh, that force is the same as this force. And this reaction force on this side is the same as that force, so the internal force has to be the same. So springs in series have the salient attribute that the forces are the same. And it's kind of an interesting, you think, okay, I have a tug of war, right? I don't know, do people outside of the United States do tug of wars? You get all your friends on one side and all your enemies on the other side of a big rope, and then you pull and you see which. Okay, people know what tug of war is, right? Oh, okay. Anyway, but they can all be friends, though. They don't have to be friends and enemies. But right, think about it, right? Yes, there are going to be different forces in between people. Okay, but if I just have a long rope, the force is the same, right? It's just a wire or a cable, right? Back from your physics days, the force is the same throughout that cable. Okay, so forces are the same. The displacements are not. Okay, and they add, right? They'll add to total, just like the potentially different forces will add to total applied force. Okay, so this justifies this little slick a move, or whatever you want to call it, right? The twirly, all right? But there are those of us who will be like, I want to see the math. All right, fine. Okay, so one way, and if you look in the old notes from, like, there's this OneNote file still hanging around, and I think it's the summer of 2023. There's a section in that OneNote file which is on the engineering-content website for spring. No, maybe it's fall of 2023. Fall of 2023. Anyway, you find that OneNote file. You go to pre-exam 1, and I have a page where I kind of covered a lot of this. Okay. But this question comes up, and if you look on one of the example exams, one of the example exam ones, I don't know which one it is, this problem came up, all right? But maybe here's a little bit more detail on it. When you have these types of systems, we can actually look back and say, oh, I want to use method of joints. And you're like, what? Yeah, I want to use method of joints. So let me see if I can change the color because it's getting all mixed together. And thank you to whoever provided this pen. I'm very appreciative. Okay, you're right there. All right. So we can write this out as follows. We put a node in there, and we say, hey, there's a force acting on that node, and I have a delta there. Okay, big whoop-de-doo. But if I look at this node, I can say that if I go to the right with my force and my displacement, okay, and this is something I think they cover more in dynamics. We don't really cover it that much. At least I hope they cover it a little bit sometimes. It depends. It depends on who's, okay, never mind. I hope nothing. This is where I kind of learned it, right? You do a little nudge, all right? So if I nudge that node to the right, then I look at the forces that are acting on it, okay? So I'm nudging it to the right. I already said I have a F, okay? And then I look at, what's happening with the springs? Let's call this, this has a K1 and this has a K2. So this could be force 1 associated with spring 1. And this could be force 2 associated with spring 2. Okay, you see that? right? So at that node, it's like we're doing it's almost like a truss, okay? We're looking at the equilibrium there, and we're going to have, well, if I say that right is positive, I'll have F minus F1 minus F2 is equal to 0 using equilibrium, okay? And then, what about the displacements? And why am I doing this? Well, I'm doing this because I have these constitutive relationships where F1 equals K1 delta 1, right? And I have F2 equals K2 delta 2. Right? So when we need to kind of merge these together, we can use geometric compatibility. Right? Now, I could also use method of superposition, all right? But this is just using geometric compatibility here. So I'm going to say that delta 1 is equal to delta, all right? And this is maybe a little controversial, but I'm also going to say that it's equal to delta 2. Okay? You're like, well, one's in compression, one's in tension. Yeah, I kind of got you there. I got you. But if I think of what's happening to that reaction force, okay, of F2, right? F2 is going in the same direction as F1, which is opposing the F, right? I can go ahead and I can kind of say, okay, these are all going to be the same. And when I do that, the algebra becomes pretty simple. What do I see? I see that I have F, so going back to the top, I can do some substitutions, right? I can say, and this is where I did a poor job planning this out, but let's just say that I have F plus, not plus, F equals K1 delta 1 plus K2 delta 2. And now I know that those deltas are all the same, and so I have K1 plus K2 times delta, right? And that's the equation for springs in parallel. So if you didn't believe my flipperoo, all right, the math and the physics bear this out. Okay. Any questions on this? This comes up a lot. People will see this and they'll get all upset. They'll be like, those are springs in series. Like, well, but it's not, because you've got two constraints and your force is not applied at the middle here. Okay. If I did apply the force at the middle, as you now know, right, this section over here goes along for the ride. Okay. So, so then you just have the spring constant associated with the K1, right? Now, I could use method of superposition, and I could say, oh, well, you know, I know that this goes along for the ride, and then I have to push back by a certain amount, okay? And then I can figure out what the force from that pushing back, so that I have zero displacement, would be in here. And that's going to, when I calculate that force out, I can figure out the effective spring constant for this location in the middle as well. So you have to be careful where you're being asked to have a displacement, right, and where the force is being applied and what the constraints are. And that's kind of rhetorical. Okay, I'm going to boldly give this back to you, okay, just so that you don't lose it. Right? And I don't think I'm going to need a 10 for the rest. Right? But I could be wrong. Okay. Let's put you over here. All right. Any questions? Any comments? Any ideas? Great. All right. So let's go on. Okay. And let's start talking about stress. So you all are very good at figuring out what internal forces are, right? You've done that a lot. We all have done it. We're all good at this. Hopefully I'm good at it too, okay? And if you have a body, or you have two bodies, right, and you like are having them like act on the surface, right, together, like they have like a perfectly nice surface, and you push these two bodies together. Or you take one body, you split it in half, and you look internally at the surface where they're interacting, okay? You can imagine that there's going to be a force, pair, action and reaction. So that would be like this big vector. Okay. Now, it turns out, right, that that force is actually distributed, right, over this cross-sectional area. Just like you think of pressure in a piston acting on the surface of one of the plates or something in it, right? On the walls, right, of the piston, and on the piston itself as it's moving up and down, right? So you've already got this idea that you can have some type of pressure distributed over an area, and that's going to be a force. So what we do is we think of now dividing all these little forces, okay, over these little areas. Okay? So those become our delta A's, or, and then as we say, oh, we're going to infinitesimally small, we can have these delta F's over these delta A's that then become, right, for the sake of doing integration or calculus, dF's over dA's. Okay? And then we could integrate, right, if we want, so if I have, all these dF's over these dA's, I can integrate, right, to figure out what that total force is. Right, so like I get, I just get my pen up, right? But anyway, right, if I can think of all these little forces acting over these areas. Okay. Now, what we call a quotient of the small force acting over a small area, that's what we call stress. Okay. And so there are all these other definitions if you want. Stress is defined as the force across a small boundary per unit area of that boundary for all orientations of the boundary. Okay. Stress is the force per unit area on a body that tends to cause it to change shape. Okay. So that kind of makes sense, right? We've been talking about forces on bars that an axial loading, and they're going to change their dimension. They're going to change their extension. Now, any questions on that? Okay. Notice, okay, that this force is coming out at an angle. Okay. So that stress that we're thinking of doesn't always just have a component that is coming out normal to the face. It could be coming out a little bit in the y direction, right? It could be coming out a little bit in the x direction, or going to the negative x direction, right? And it could be a lot of it, if z is the face, right, then maybe a lot of it, most of it could, in this case, could be coming out in the z direction. Okay? So what we see here are that stresses are defined on a face, okay, but they can be associated, or there can be different directions associated with them. Okay? So let's dig into this a little bit more. I can think of now some delta F as a vector, and we can think of this z face, all right? So z is coming out of that face. It's orthogonal to it, so that would be a z face. We can think of an area in the z direction. And we can think of this kind of overall force, right, also as having components in x, y, and z. Now, there's something that we can define as a traction vector, okay, and this traction vector is essentially this force divided by this delta A. Okay, so this quotient here. Okay, and that traction vector has with it stresses in the x and the y and the z directions. Okay, so now what we're getting to is that the stresses, okay, so if you have a traction vector, what are the units of this Well, the units of this are going to be force per area. Okay? So that's going to be, you know, what you're familiar with stress, right? Or newtons per meter squared, something of that nature. And the components, okay, that this vector would represent, those are what are going to be our stresses. Okay, so we have now a traction vector, okay, and we have the components, which I haven't written out yet, being associated with stress. Okay, so let's look at it. Here we have the traction vector, and now we're saying let's break it down into the I, j, and k directions, right? So the x, y, z directions. And the stress is this quotient of a small force acting over an area. And what we are going to say is that, again, these components in the I, j, k direction, these are stresses. And these stresses, in this case, you see, it's got a component in the x direction, okay, acting on the z face. Okay, this has a component in the y direction acting on the z face. This has a component in the z direction acting on the z face. Okay, so we can write this traction vector in terms of these stresses, okay, and it looks, yes. It looks like this. Okay. Now, so let's talk about this a little bit, right? So you see, here is the z face. This is a stress on the z face. They're all on the z face in this case. All on the z face. Okay. And we have it in the x direction, the y direction, and the z direction. So you can see that, okay, this is a component on the z face in the x direction. This is a component on the z face in the y direction, that green one right there. And this is a component in the z direction on the z face, that one right there. Okay. So those are stresses. And what we can introduce is a notation. Okay, so these are not the sigma ij, they're not the same I hat, j hat, k hat. All right, these are just indices now. I'm sorry, it's maybe a little confusing. Okay, all right. So this is I hat, j hat, k hat. This is little just I and j. Right. So the first subscript is what we use to specify the direction of the face. Okay. So which face have we? Which face is this? This is the z face. So all these are z faces. The second subscript specifies the direction of the stress. Okay? And as I said before, they're not, these I and j are not these I hat, j hat. Okay. Now, if I'm at a location in a structure, okay, there's a material there, I can begin to think of my structure as being made up of lots of cubes, lots of voxels, lots of elements. Okay. Now, in this case, we've only talked about the z face. All right, but we can think about a cube in the material that will have an x face, a y face, and a z face. Right? And there actually will be negative x, negative y, negative z. Right? So a cube has 6 sides. Do these indices, can I use them to describe the 3-dimensional nature of this problem? Can I describe every face of a cube with I and j, lowercase, not I hat, j hat? The answer is yes, okay? A lot of times, I was talking to one of our esteemed fluid mechanics professors, and he said at the end of the semester, and in fluid mechanics they use tensors, which we'll talk about a little bit today. A student came up to me and said, how come we don't have sigma ijk? We've got 3 dimensions. Don't we need an ijk? And he was like, oh my goodness, we went through a whole semester. All right, so don't do this. Yes, the sigma subscript lowercase I and j will describe a 3-dimensional state of stress. Okay? This lowercase I and this lowercase j, right, what we do is we plug in essentially 1, 2, 3, x, y, z. All right. That reminds me, I think one of the Jackson 5 just passed away, right? A, B, C, you know me. 1, 2, 3, something like that. 1, 2, 3. Isn't that? Don't they have that song? All right. Anyway, so maybe as a little tribute to the Jackson 5, right? We can get 3-dimensionality by x, y, z. All right, popping them into the lowercase I and j. Okay. I think this will become a little more clear on the next slide. All right. So let's talk about. Okay. Well, before I do this, notice that sigma zx and sigma zy are not acting parallel, or they're not acting, collinear with the direction of the face. Okay, that's kind of you're like, oh, duh, I got that, right? You told me it's in the z direction, or in the x direction on the z face. Okay. Oh yeah, and it's in the zy would be in the y direction on the z face. Okay, yes. All right. But typically, I feel much more comfortable dealing with forces or stresses that are acting in the same direction as the face. So I like my sigma xx. I like my sigma yy. I like my sigma zz. I probably shouldn't have preferences. Okay. If I had to pick, right? These are what we call normal stresses. When the direction of the stress is in line with the face. Okay, so sigma zz is what we call normal stress. And that's probably ironic because I'm not a very normal person. I'm probably, more not normal, but I like these normal stresses. Okay? Now, when that happens, we don't write zz, because this is repetitive. So if you just see a sigma z, you know that means sigma zz. That's a normal stress. And maybe it's one less thing to sleep on during class. You don't have not as much snoring. All right. Similarly, if I have this element, I have these other faces, x and y, right, which we were just talking about in a structure, and I can get stresses that are in these y direction and x direction. Okay? And so the normal stresses are going to be sigma x, sigma y, and sigma z. Just like that. Okay? And there we go. Yeah, they look kind of like this. All right. Now, these are forces divided by areas. If you saw this cube and I put these little forces divided by areas on a cube and I held it in space, what's going to happen? Yes. It's going to move. It's going to accelerate, in fact. That's a problem, right? Because in this class, we're doing statics. Okay, so what happens is there has to be equilibrium. Okay, and And so what does that mean? That means that on the opposite side of the cube, there has to be another force divided by that area, okay, or stress, right, that is going to be counteracting the stresses to be able to keep it balanced. Right? And we've kind of, this is, if you need to, just go back, I've been doing bars for a long time now. Well, I've been doing bars for, I've been thinking about internal forces and bars for a semester and a couple weeks. So, just think this is a bar, right? And this is a little bit of foreshadowing. If I just have a bar with a force on it, and it has some cross-sectional area, right? And I'm just pulling it like this, and I say this is the x direction, right, on the bar, then, well, what's happening? I've got a sigma x in there, right? So no one told you. We've been dealing with stresses the whole time, right? We've been dealing with stresses the whole time. Yeah, I mean, you probably already figured that out, but we can think of, a bar or, 3 bars, right, where we have this 3-dimensional state of stress, if you like. Now, there are conventions, okay, associated with these normal stresses. If this is the x face, this is the minus x face. If this is the y face, the other one is the minus y. Right? Why is that? Well, because remember that we define faces in terms of the normal vector that's coming out of the face. Okay? So we've got a minus z face that's opposed to the z face. All right? And so if we want to get kind of technical, we would say that, okay, this is a sigma minus x, so that's the minus x face, and that stress is acting in the minus x direction. This is a sigma minus y, this is a sigma minus z. Okay? And then there's this nice little kind of thing. We define the resulting stress component to be positive when a positively directed force component acts on a positive face. Alternatively, a positive stress component results when a negatively directed force component acts on a negative face. By consideration of action and reaction, we see that the definition follows from the first. When a force component acts on a positive face, the resulting stress component will be negative. Okay? So what is that saying? Saying, don't stress about this. Okay? Just do sigma minus x is going to be the same as sigma x. Sigma minus y is the same as sigma y, and sigma minus z is the same as sigma z. Right? And this is also not too dissimilar of a concept from what you've thought about, right? Remember when we take slices and we do the cover-up method and we say, hey, we're going to cover the right side up. All right? And we have a normal force coming out of it. And then you say, oh, I'm doing the cover-up method and I'm going to do the left side, cover that up. Right? And then I got a vector going the opposite direction for the force. We know they're describing the same behavior. Right? They're just on different faces. Right? So this kind of helps us again be consistent and remember our notation. Okay. So if we go now and just introduce a little bit of math. Okay. We can say if we have a force on a DAX, right, or we're interested in a force on a larger area x, AX, right, so we have a little force over a little area, or we have a lot of force on a larger area, we can begin to think of breaking up that force, right, into these stresses and then integrating those stresses over the area of interest, and that's going to equal the force. Yes?
What's the difference between a stress and just a pressure?
Good question. What did I tell you about pressures in physics in terms of how they act on surfaces? Okay, yeah, okay, true. What about the direction?
It's all the same direction.
Yes, well, it depends. Yeah, it's always normal. Okay, pressure is always normal to the surface. All right, so you can have like this curved cylinder, you remember, and then like boom, 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 the force you know, you have this the pressures acting normal everywhere on that, and then like it doesn't go anywhere, right? Because you've got equilibrium essentially, right? And you remember taking effective cross sections. Maybe you did that, right? So like, what's the effective area that this pressure is acting over? And we're going to think about it that way. Yeah, pressures and stresses are very similar. Okay. What we're introducing here, and I'm focusing a lot on normal stresses. So yeah, I would say normal stresses are very akin to pressures. Okay. With here though, we're going to a step further and saying, yeah, you know, I could have a cube, like so. Let's say you have a cube underwater. Okay, and you remember rho gh, maybe for your pressure. So as that cube goes further and further down, right, the pressure it builds up, and it's the same on every side. Because we're assuming the cube is not like really, really large, right? Because then you have to do that other problem, right, where you have this linear gradation with the pressure, right? You remember that from physics? And you're like, oh, crud, now I've got to like, I got to figure out where the center of pressure is, and it's not fun. Okay, so, but it's actually very, very similar to what we're doing here. Okay, so it's different from pressure in that it's pretty simple to imagine that now I've got a cube not under pressure, and I pull on one face and I push on another face. I have two normal stresses that are not the same. Whereas if it were underwater, essentially that's called hydrostatic loading. The stress would be all the same on every single side. Okay, and then we're going to get to another thing. Remember, stress is also, so just that's for normal stresses. Stress is also describe a force or, a small force that's acting parallel. So if this is the face, right, this is the vector coming out. And I can also think about stresses that are acting parallel to the surface. And that's something a pressure cannot do. It cannot do that. All right, so this is one way of summing up the stresses, or summing, or integrating, okay? And we can say that the summation of forces for equilibrium to be true has to be equal to 0. And so we can see that, okay, if I've got this integration of sigma x dAx minus this integration of this sigma minus x dAx equals 0, these have to be equal to 0, okay? And we can, of course, do this on all 6 faces. Right. How are we doing on time? Probably slow. Not too slow. This class doesn't go super fast. I mean, I don't have I can get through it. Okay, so here is kind of an example. All right, we're going to say that we have a bar. And this is kind of like, you know, we're just, again, right? You're like, oh, I already know the answer because we've been doing this now. And actually, I was kind of doing this at the beginning of the class. Okay? So, what are the normal stresses in the 2 sections of this bar? Okay? So let's do it out. No one needs to shout it out right now. Okay? So if we're looking at external equilibrium, right, that's usually the first step. We'll say, okay, there's a force, acting at this location, and there's got to be a reaction force from the wall, okay? And we have a summation of the forces, and the x is going to be equal to 0, so F minus R wall equals 0, so I know that the R wall is equal to F. And we now do a slice, we do internal equilibrium, and we say, all right, so what's going on inside here? We have R wall, and we have some internal, we'll call F sub x, all right? And we say that, well, F sub x has got to be equal to R wall, which is equal to F. So that's a force. And now if I go to the next region, all right, so this is describing what's happening on the left. Now if I look at what's happening on the right, what is the internal force there? I like that, 0, yes, that's correct, okay? So that force is 0, okay? And now let's go a little bit 3D-ish. Again, this may be a little bit extreme for a lot of you, okay? But we're just trying to make the point. That AX face, right? So that was over, let's say it was over here. Okay, let's say that this is going to be what we're describing here. We have FX over AX. So for this region, we can just say that the sigma x is equal to force over the cross-sectional area. Okay. Any questions on that? Pretty straightforward. And we'll call that region 1. For region 2, all right, which we'll say is describing this. Well, if fx is equal to 0, then we'll just say that we have 0 divided by that area, so that would be sigma x equals 0, right? Nice and easy, simple, okay, goodness. So in general, for bars, okay, we can kind of write out that there's this axial stress, and we'll call it sigma sub I, right, where it's the force in that given direction divided by the area in that direction. And we are, in this class, generally assuming that the force, the normal force across it, is uniform. Okay, that's not necessarily 100% true, okay? But for our intents and purposes, we're going to think about the average force. So, if we do a specific example with some numbers, all right, we can have a cross-sectional area, okay, which is 1 centimeter by 1 centimeter, okay, and let's say we have a force. Okay, we have our sigma x equals the force divided by the cross-sectional area, and we do this out, and we have 1,000 newtons divided by 1 centimeter by 1 centimeter, all right, and then we say, oh, okay, we had to do a dimensional analysis, right, and this is what we get, and then we say it's 10 to the 7th pascals, and that's equal to 10 megapascals, all right? And if we do the opposite direction, if it's a negative 1,000, then we can say that the sigma x is going to be the negative of what we just had. Okay. Any questions on this? There should be a negative sign right there. Let me see if I can put that in. All right, see? Negative. Okay, so any questions on this? Pretty straightforward. Okay, if the units hang you up, you can't do it on the exam. I guess maybe some of your calculators are that smart. But if, you know, I think I pointed this out in one of the videos for the assignments. I think that of the search engines, Google is the easiest to handle. All right, in terms, it handles units the most easily. So we said we have 1,000 newtons divided by 1 centimeter times 1 centimeter, okay? And so it tells us, it keeps track of things kind of nicely, and then you can say, oh, I want it in units of megapascals, all right, and it will do all that conversion for you, okay? So if you're hung up on the units, you can use Google to do that, all right? That's not necessarily the you know, the most thoughtful way to do things, but it does keep track of units for you. Mega 10 to the 6, right? What else? Centimeters. Yeah, I think the conversions are all good. Conversions are all good. Okay. So there's a question in the homework about this. It's pretty straightforward, but you know, it gives everyone a chance to get there. In terms of, oops, where did my mouse go? Okay. Yeah, there's another question. So example 2, 4.2 is just what happens if it's reversed. So we did that already. Okay. here's some common conversions. All right, so if we stay all metric, everything's happy. All right, but sometimes, so here's your pressures. Here are your pressures. So if you have 1 psi, that's like 6.89 kPa. This one comes up probably more in the class than some of the others. So 6.89 megapascals is equal to 1 ksi. So ksi is 1 kilo-psi. So 1,000 psi is equal to 6.89 megapascals. Yeah, so if you think in terms of sound waves, so these are pressure waves, right? These are not like the slinky going across, although you can think of it that way, right? You know, when I say slinky going across the room, you have some ideas from your physics class, right? Where the guy is like, hey, let's look at the standing waves. Okay, these are compressive waves. Okay, so the air is going back and forth like this as I'm speaking, as you're moving, as we're all generating sound. And these pressure waves have remarkably low values, okay? But they, of course, a jet engine is going to blow out our ears pretty much, right? But that pressure, the compressive wave that it produces is not that. It's interesting that it's that small. Whereas the stresses that we're thinking of in this class are typically in the megapascal range. Not always. We get some in the kilopascal range. And then we'll introduce another thing that gets into the gigapascal when we think of elastic moduli. But this gives you an idea of the types of stresses that we're going to be dealing with. Okay. And then there will be another kind of question to go back from megapascals to force. All right? It's just to get everybody set up. Now, question number 5. All right, and I'll go through this a little bit more. This one is just tricky because it's a truss problem. Okay, so if you like, all right, you can just use the Colab script that's available to solve. The Colab script is using a method of joints to solve the problem, and then you can figure out, once you know, because in a truss, right, remember in a truss, it only supports an axial force. Each member does, right? The joints can have, or the nodes, right, they can have, compressive forces and tensile forces acting on them. We kind of talked about this. But the members themselves in that truss system only support an axial load. So this is an opportunity to think about calculating out what the normal stress in a member is. But what you have to know, you need to know the force and you need to know the cross-sectional area. Why? Maybe I skip this. Why do I even calculate stresses? Why are we calculating stress? Yes, Michael.
Because for different materials, the structure will change.
Okay, so the structure will change, yes. So stress is associated with deformation, and that's what we call strain. We're going to talk about that in a second, okay? But why else? And why else? Yes?
The more material you have in a cross-section, the more load you can support. So if you calculate stress, you know whether it will fail based on the tensile.
Yes, right? Okay, so the tensile strength, right, is not something that we've talked about. And there are different types of tensile strengths, which we'll talk about in a little bit. Okay? And what's your name? Aiden. So what Aiden is saying, though, is that essentially every material has a limit. Okay, it has a limit to the amount of stress that it can handle. So now, you spent a semester in statics thinking about, okay, this is the force, this is the force, this is the moment, this is the moment, this is the force, right, inside. But you had no idea if these forces were going to lead to the structure breaking. Okay? But now that we can calculate stresses, if I say this material that you're using cannot handle more than this amount of stress, we have an idea of, is it going to break or not? So that is one of the key reasons that we are trying to understand stresses. We're trying to understand stresses so that we understand the limits. And we're also trying to understand stresses so we understand deformation. Okay? Usually, as mechanical engineers, braking is more hazardous than stretching a lot. Okay? But stretching a lot often is associated with braking. Okay? So we want to keep both in mind. Okay. Let's see, where are we? I think it's time to talk about strain. So, normal strain. Strain represents the displacement between particles in the body relative to a reference length. Okay, so what are we talking about? We know what displacement is. Okay, we know what it looks like. We know what deformation kind of looks like. What is this strain, though? This strain is talking about displacement, and it's also talking about a reference length. So let's imagine that I have this little box or square or rectangle that we'll say, here is just an XY profile. So Z could be coming out of the board, all right, if I wanted. And let's say it's infinitesimally small. So that means that I've got a dx for my width and I've got a dy for my height. If now, magically somehow, we go to this new state where I've got some displacement on the right side. Okay? So we're saying essentially that this has been fixed to these coordinate systems and this is now stretched out. Okay? And that new displacement is delta x. All right? And we just spent time calculating out what these delta x's could be, or deltas could be for bars. The normal strain is going to be defined on an x face. So where's the x face? Well, if this were 3D, right? There would be a normal vector in the x direction coming off of that face. And that'd be the x face, and it's happening in the x direction. So now we introduce a new parameter called epsilon, and epsilon sub xx is going to be this ratio of the delta over the original length. And epsilon yy, if there were one, okay, which I haven't drawn, but let's say that I had something in the vertical direction, would be a delta y over the dy. And just like the indices that we use for stress indicated, the first subscript is the face, the second subscript is the direction. Okay? Now, what are the dimensions? What are the units of this so-called strain? There aren't any. Okay, what's your name? Marty. Okay, Marty, yeah, I agree with you, right? These are dimensionless. So, could you have two bars experiencing the same normal strain, but having different displacements? You could. Why is that? What would be that scenario?
I mean, one reason could just be different units. That would be the simple answer. But there's also just different ratios.
Okay.
Because it technically is just like a ratio to how big the thing is to how far it goes.
Yeah, exactly. I was going to say the length, but you said how big. Let's just say how big, right? So if I have a bar that's really long and it has a given amount of strain, let's say it's 1 microstrain, okay, and it's really long. And I have a short bar that has that same strain, 1 microstrain. That's a small strain, 100 microstrain maybe. Okay, that's maybe more along the lines of what we deal with in the class. But yeah, we can get down to single microstrain. then the longer bar is going to exhibit a lot more displacement than the shorter bar. Okay? But they still have the same amount of strain. Now, if they have the same cross-sectional area, okay, what's cool is that that force associated with those strains could be constant. Okay, it could be the same amount of force in either case, but the longer one has more displacement but has the same strain as the shorter one, which has less displacement. Okay. So once again, you get a chance to look at some problems where we have some displacement, okay, and we're going to figure out what the strain is. Okay, so here we could say, okay, epsilon xx is equal to the delta over the L, and if I have 1 millimeter over a meter of length, all right, so the length was a meter, and the delta is 1 millimeter, okay, then I have the opportunity, right, to make sure my units are good, okay, and it comes out to 10 minus 3. Okay. Often strain is reported in a percent, okay, it can be, or it's reported in microstrain. Okay. So if delta was the opposite, then the strain would be opposite as well. So units of strain, dimensionless, we use scientific notation, we use percentage, we use microstrain. So 100 microstrain is equal to 0.01%, or equal to 10 to the minus 4. And common values for strain, metal alloys are going to be less than 0.1%, thermoplastics less than 1%, and then the elastomers and the rubbers, they can be greater than 10%. So your rubber bands are going to be stretching a lot more than your thermoplastics or your metals or alloys. And I've been having issues with my shoulders lately from overuse, essentially because of surfing. And so I found myself having to do these types of exercises, and I'm not as consistent as I should be, right? But I'm just amazed at how many reps these rubber bands can take and how much they stretch. It's a lot of fun. Okay, so anyway. All right. Okay, so once again, we have an opportunity on the homework to calculate the strain, and we're thinking. And so, one of the key terms is change of length, right? So if they say, hey, this is the initial length, this is the final length, right? Then I need to know the difference, and that's what I'm going to divide by the initial length to calculate out what the strain is. Okay, now, shear stress. We're not going to talk about shear stress in as much depth as we will get to later in the class. Okay? Shear stress is, though, the dominant mode of failure for many metals. So the metals, and I'm kind of jumping over some stuff, but metals often fail because of distortion, and that's usually more closely linked to shear stress than to normal stress. Okay, and so it's important to be able to kind of calculate and understand what shear stress is, and we'll do that in a variety of different structures. Namely, well, maybe not a variety, in a couple. We'll think about shear stress mostly in twisting of shafts or rods, and also along beams. Okay, so those will be the primary ones that we think about when we think about shear stress. But remember, we had these stresses that are acting parallel to the face. Right? So we have an X face, Y face, Z face. If the force, the small force that we're interested in, is acting parallel to that face, which parallel does not mean in the same direction as that face, although it kind of, you're like, it kind of is parallel. No, we mean parallel to the face, not the direction of the face. We mean to the face itself. Not collinear with the direction. Okay? So, this is when you're going to have these off terms, like a sigma zx, or a sigma yz, or a sigma, what am I forgetting? xy, yeah, all right? So you have these three off terms, and then you flip them, you can have like 6, because you can double it, because you could do xz and zx, and yz and zy, and xy and yx, okay? And it turns out that, if you know xz, you also know zx, but at least for a nice material that's that we're using in this class called isotropic and linear. If we look at a projection, and I guess I got to say before that, we designate another Greek variable for describing these shear stresses, and that is, what's that Greek variable? The orange one? Tau, okay? So you're going to see for shear stress we use tau, okay? For the normal stresses we use sigma. And in some cases, though, you'll see that sigma does get used when we describe tensors and various things. It does get used it can be used in all cases, right? But if you see a sigma xz, all right, that's a shear stress, right? So you could write tau xz, but you would never see someone use a tau, like a tau x. This doesn't exist. Like, they don't do that. Okay, all right, that's going to be a sigma x. All right, so if we look at a 2D projection of the xz plane. So what is the xz plane, right? Would be like this plane coming out here. So I'm like looking at this thing, and it's like that plane. We can draw out an element with a point, and we can say we have a z direction and we have an x direction, and we can say, okay, there's a tau zx. So you see this is the z face in the x direction. Okay, this is the minus z face on this side in the minus x direction. So if we look at equilibrium on this element, and we say, okay, tau zx is acting on the az face, and tau minus z minus x is acting on the minus z face, all right, or minus daz, all right, this has got to be equal to 0. This means that tau zx has to be equal to tau minus z minus x. So we've established something, just like we said, we don't write sigma minus x, okay? We don't write tau minus z minus x. Okay? Now, if we look at something in the moments, all right, and we're going to say, if we got some moments here, this is going to be in the y direction. So we have an x cross, so we have x, all right, and we have our z, all right. So hold on, let me make sure I'm looking at the same way you are. Okay, so we've got our x and our z. So y, right, is my middle finger. I'm sticking my middle finger out at you. Okay, that's y. All right, so that's coming out of the board. Okay, and when I do that, we have also these lengths, dz and dx. And when we do these moments, okay, we can calculate out the equilibrium here. Okay, we need the xz term. Okay, so you see this is on the x face and the z, and we need the minus x minus z term also to keep this thing from accelerating in its angular velocity. Do you see that? If I just had, let me go back. If I just have these two stresses, shear stresses, acting on the element, what happens? This thing's going to want to rotate. It's going to accelerate. Can't have that. So I've got to have, whenever I've got a tau zx, I've got to have a tau xz. All right? And this simple equilibrium demonstrates this point. Okay, so we've got essentially that tau xz equals tau minus x minus z, and tau zx equals tau xz. All right, any questions on this? So now you can think about shear stress. Now, for an element in space, right, we can draw out all these shear stresses. Right, now it's getting a little heavy, right? Like, where did all these arrows come from? Okay. Fortunately, we do mostly 2.5D problems. Okay, so we're not going to go super ballistic, but there are going to, when we do combined learning, we will have to be able to think in 3D. Okay, but you're going to be drawing faces, not these types of faces. You're going to be drawing faces of the cube that are appropriate, and you're going to be putting these arrows on them. Okay, so arrows will either be coming out of the sides of the cube, and the top or the bottom, and those will be the normal stresses, and then parallel or like along the faces, that's where you have the shear stresses. Any questions up to this point? Okay, so there'll be some, I think there are a couple problems that we get to do. Yeah, this one is, okay, which ones are equivalent to tau xy? Well, okay, yx is, yz, not, I mean, it could be, but not always, right? And then there's this other notation. Sometimes instead of doing sigma, or sometimes instead of doing tau, we, like I said before, you go back to sigma. And sometimes instead of using x and y, we use 1, 2. All right, so x is 1, y is 2, z is 3. Okay? So you could see that, all right, tau xy could also be equal to sigma 2, 1. Could be equal to sigma 1, 2. It could be equal to minus y minus x. And it could be equal to tau xy. All right, so just introducing the notation. Okay, so now we've got this idea of what a normal stress does to a bar, right? We covered that, right? A normal stress is going to be associated with a force, and that force is going to cause there to be some axial loading and then some axial displacement of one bar relative to the other. And I can calculate out what the normal strain is, right? The normal strain is going to be, what's the change in length over the initial length? So there's a parallel, right? There's a parallel between normal stress and normal strain. Likewise, there is a parallel between shear stress and shear strain. So if we take this 2D box again, and we think about moving the top face. Okay, this is maybe a little counterintuitive, right? But this top face, let's say it moves over delta. Okay, so this point here moved to here. This point here moved to here. Okay, and now I've shifted this thing like this. If I blow it up a little bit bigger, okay, it's the same thing, and I look at the angles, all right? And that, anyone want to tell me what that Greek letter is? Is anyone here from Greece? Okay, so what letter is that?
Gamma.
Gamma, all right? Awesomeness. Thank you. It's Martin, right? Huh?
Mark.
Marty, okay, Marty, all right? So, that's gamma, all right? And we can write that the tangent of gamma is going to be this delta over dy, right? That's the opposite over the adjacent with the way we define gamma. And it turns out that we typically, in this class, fortunately, we have very small angles. Okay? So we will be able to use the small angle approximation, which says that the shear strain is going to be delta over dy. And how do we write this? We write it as gamma xy. All right? So here, all right, you recall that if we had, well, how do we want to put it? This is essentially the gamma between the x and the y direction. And I don't have a pencil. Let me see if I can. Let me see here. Yeah, I don't have a pencil. Okay, but let me see if I can kind of draw it with my finger. Hold on. Okay, so if I have, no, I can't see it. I think it's that one. Yeah, that's one. Okay, I have this box, okay, and I draw my shear stresses like this. Okay. This element is going to distort like that. Okay. If this, the way we defined it before, this is y and this is x, like that. Okay. Do you see that on the x face, whoops, on the x face, this is the x face, in the y direction, I have a tau xy. Okay? What we've described here with this deformation is this gamma in there, right? We have a tau xy is somehow proportional, okay? That's not gamma, that's alpha, right? To gamma xy, like that, okay? And if you didn't know what time it is, now you do. All right, so wrapping things up, there's something called a stress tensor, which is just a matrix. Well, it's more than a matrix, all right? And there's some videos on what the heck is a stress tensor, okay? But what we do is we fill up a matrix. We fill up a matrix with all these components of stress, okay? And the meat of the matter is a tensor is a special type of matrix that preserves its information as we rotate the element. Okay, and you can watch those videos. And we'll talk more about this a lot in the future. All right, so that covers stress and strain for today. We'll talk about stress and strain through the rest of the course. Every single day now, we will talk about stress and strain, or one or the other. Okay? Thank you for coming. Have a wonderful day. Remember, there's an assignment due on Friday. Okay? Yes. Oh, attendance. Oh, shoot. You guys, I'm sorry. Oh, my goodness. We almost got out of it. Oh. Okay, here's the attendance. Hold on. Yeah. Okay. Yes, please do the attendance. It's 1:30, so you got it. You can do it. Whoops, that's the wrong. Well, that's fine. It'll be unique. All right. Thank you, everybody. Have a good day. You too. Yeah. the pre-lab. Yeah, so let me just